Hello everyone, I am Mohammed. Today, me and my friends will give presentation on our project. The project title is Drinking Water Generation from Atmospheric Air. We have designed and fabricated a prototype of it under the guidance of our assistant professor Taufik Chansha. He was very helpful and cooperative with us, and whenever we used to face any difficulties, he would help us to rectify and eliminate the problem in the project. The contents. The contents which are included in a project are abstract, literature survey, design, working principle, calculation, cost, advantages, and conclusion. The topics which are allocated to me are abstract, literature survey, design. So I'll begin with the first slide, that is the abstract. So as we know, water scarcity is one of the burning issues in today's world. Even though 70% of the Earth's surface is covered with water, only 2.5% is fit for drinking. Okay, the acute problem of water shortage is mainly faced by countries which are having a long coastline and island nations. They do not have adequate fresh water supplies such as rivers, ponds, etc. As a result, most of these countries, they meet demands of water by desalination of seawater, and it's a very costly process. So the main aim of a project was to create a portable device used to meet water requirement. So the device will first condense water present in the atmosphere, then purify it so that it can be used for drinking. So basically, drinking water generation from atmospheric air, it's a device that employs dehumidification or condensation technique that extracts water from humidity of air. It's that simple. Water is filtered and purified through filters. So basically we have taken three things into account. That is the portability of water, simplicity, and safety. We move on with the next slide. That is the literature survey. From the web, above mentioned paper, I got to know the detailed information about the properties of water. That is the dry bulb temperature. We have the wet bulb temperature and the dew point temperature. We infer that even though dehumidification unit using vapor compressor efficient system is more effective, this type of generator we can implement in extreme situation like during floods or in desert or in rural areas. We move on with the next slide, that is the design. So as you can see in the slide, there is a prototype model and the frame. Okay, our prototype model consists of a frame which supports the compressor, condenser, evaporator, coils, tap, wire, etc. So I'll briefly explain the parts in it. So the first is the compressor. As you know, the compressor, it's a device which increases the pressure of the gas by reducing the volume. So in our project, we have used gas compressor. So then the next is the evaporator. It converts the liquid form of chemical substance into water. Then we have the condenser. It's a heat exchanging section. It has a heat exchanging section to cool down and condense the incoming refrigerant vapor into liquid. Then there is a motor situated, as you can see, which is 5 horsepower, and usually it withdraws the current of 220 volts. Okay, so it is accordingly set up in the frame as you can see in the prototype model. So the remaining slides will be explained by my teammates. Thank you.
The project is basically used where there is a lot amount of humidification in the air. Because of evaporation, basically the atmospheric air, which is completely humidified during summer, is being taken into the system from air filters. These air filters is basically used to purify the air and remove the impurities which are present in it. Later on, it is passed to the evaporator where a coil in which of refrigerant Ppt 12 is used. These refrigerant will seek in the heat which has been present in the air, and the moisture present in the air will be converted to water. This is the diagrammatic view. Here we have converted the vapor content into water. This water has been stored into the storage tank. Now, due to the heat taken in by the evaporator, the coil which has refrigerant, that refrigerant converts from liquid to vapor form. Here, the temperature increases. This vapor of refrigerant is then passed to the compressor, where the compressor compresses the vapor, wherein the pressure of the refrigerant increases. Compressor is basically driven by a motor. So, the compressor basically uses electricity as a source of compressing the refrigerant. It is then passed to the condenser where it is condensed into a vapor again. The refrigerant of liquid from vapor refrigerant is converted to liquid refrigerant in the condenser, wherein the temperature of the refrigerant decreases, but the pressure does not change. To decrease the pressure, we are using expansion valves. That expansion valves will bring back the pressure to its original position. It is then passed again to the evaporator. The cycle continues. So in the condition end, we are going to use a blowers which rejects the heat to the atmosphere. Now the basic important thing which comes into consideration is that will it affect the air by extracting the moisture and converting it to water? No, because what is happening here is this system is basically used during summer season. So whatever amount of humidification takes place is because of evaporation. So whatever the moisture contained in summer will be present in air is because of the water evaporated through the lakes and rivers, not because of what it contains. So water will be having its own moisture content. We are adding certain moisture due to evaporation. So we are only harnessing the moisture content which has been evaporated and not that which is already present in the air naturally. And the main advantage is we are indirectly purifying the air because we are only taking the moisture content and we are expelling the remaining air to the atmosphere. In between, we are going to use air filter which also is used to purify the air purpose. In these, we are going to use two concepts: air purification as well as conversion of vapor moisture content of air to water using dehumidification.
Hello everyone, my name is Mohammed Asad Shaikh, and I'll be explaining the calculation part of the project. So as you can see, the first one is the calculation for the dew point temperature. So this calculation form an important part of this project, as this help us to determine at what temperature the Peltier device must be maintained in order to condense the humidity present in the given atmospheric condition. So I'll tell you what the dew point temperature is. So the dew point temperature is the temperature at which humidity in the air starts condensing at the same rate at which it is evaporating at a given constant pressure. So as you can see, this is the two formulas which we have been used to calculate the dew point temperature. So first one, I have shown you the sample calculation using the dry bulb temperature at 30 degrees Celsius and relative humidity at 45%. So in which formulas there is a term B and the term C. So these are the constant values in the dew point temperature. So the B value is 17.61 and the C value is 243.50 degrees Celsius. So the above two formulas are used to calculate the dew point temperature for different atmospheric condition at which the device may be subjected to operate. So first we have got the dew point temperature, that is 16.77 degrees Celsius, using the data, that is dry bulb temperature at 30 degrees Celsius and relative humidity at 45%. So I'll show you the second slide of a calculation, which is for the calculation of amount of water present in 1 meter cube of air. Okay, that is for the calculation of amount of water present here, we have to calculate the humidity ratio. So humidity ratio gives the volume of a water present in 1 meter cube of air. Also, we know that 1 meter cube is equal to the 1000 liters. Thus, multiplying the humidity ratio by 1000 gives the maximum amount of a water that is present in 1 meter cube of air. So, for the calculation of water present in the atmospheric air, first we have to calculate the partial pressure of water. That is relative humidity divided by 100 into P. That P is a saturation pressure that we have taken from steam table. And yeah, I have shown you the sample calculation taking the dry bulb temperature 30 degrees Celsius and the relative humidity is at 50%. First we have calculated the partial pressure of water. That saturation pressure we have taken from a steam table, and second calculation is the humidity ratio. That is, I have shown you the formula for a humidity ratio. Therefore, the amount of liter present in 1 meter cube of atmospheric air, that we have multiplied by 1000. So according to data, that is dry bulb temperature is 30 degrees Celsius and the relative humidity is 50%. We have calculated in 1 meter cube of atmospheric air, that is around 13 liter of water is present. We can extract that amount of water. So the second slide is about the table of dew point temperature calculation for different atmospheric condition. That is as follows, that we have collected from. And this third slide is of cost expenditure. The cost details of this project we have given. So the second slides will be explained by my partner Niklesh.
Hello everyone, my name is KAMBLE. Today I am going to explain the advantages of a project. Advantages: it can help to solve the problems of water scarcity. It is a portable and can be used almost anywhere. We get pure drinking water. Simple in design, it also acts as a dehumidifier. Applications: water generator is a device which can be implemented from extreme situations to use during floods in desert areas and in rural areas. Our device can be used in extreme situations where floods occurs, where in desert areas and in rural areas where water scarcity is a main problem. It can be implemented for industrial development where the water is a matter of crisis. As we know that many industries are present at the outskirts of the cities where water scarcity is a problem, hence our device can be used there. It acts as a backup device when breakdown of main water supply. When there is scarcity of pure drinking water, it can act as a backup device. Future scope: system can be designed that encounters high power solar cells and also has the adroitness to store the excess energy during the daylight that is to be used at night. For large scale implementation, RO and UV water filters can be used for producing such water that meets the standards of WHO and BIS easily. Systems can be used in defense systems, also as a portable water generator in remote locations. Conclusion: applying this system is a highly humid region. Almost 1 liter of condensed water can be produced per hour during the daylight. This is a promising result. Then a more enhanced system can be designed that the device uses the principle of latent heat to convert water vapor molecules into water droplets. These are some of the reference papers through which we came to know about the project. Thank you.